All right, hello everybody. So my name is Alexis, and my proof today is going to be on the five Platonic solids. And a little rundown is that we're going to be going over the history, some properties, axioms, examples and non-examples, and our formal proof. So jumping right in, we have the history of the Platonic solids, and there are five Platonic solids that were introduced by Plato in 873 BCE, and they were originally represented as all known forms of matter, so earth, air, water, fire, and ether, which is the upper regions of space. And then a little later, Euclid was able to verify his findings and solidify that there only exist five, and the Platonic solids represented the five elements because it was believed that these five shapes were connected to the cosmos. So the octahedron is supposed to represent air, and it is connected to the heart chakra, which promotes love and compassion and giving you inner peace. The cube, which represents earth, it's also known as the hexahedron because it has six sides, and it represents earth and signifies safety and containment and aligning with the root chakra, which is at your feet. The tetrahedron is representing fire and is considered the most stable of the Platonic solids, and so it represents more focus and strategy and is aligned with the solar plexus, which is around your midsection. The dodecahedron represents the universe and is associated with the upper chakras, which are your throat, your eye, your third eye, and your crown, which helps with invention. And lastly, the icosahedron represents water and is a carrier of emotional energy, which is linking your mind and your heart, and it is aligned with a sacral chakra. So before we get into the Platonic solids in general, we're going to talk about regular polyhedrons. So a regular polyhedron is a 3D shape whose faces are regular polygons, and all of the side lengths and angles must be equal for them to be considered regular. They can be of mixed polygons, but we'll get into further specifics about like the rules for Platonic solids. However, in general, regular polyhedra must have at least three faces meeting at a vertex, and the total angles of the vertex must be less than 360 degrees, which we'll get into a little bit later. We also have irregular polyhedrons, and these are quite the opposite. They're uneven, they don't really conform to any of the regular polygon constructions. They are of mixed polygons, but sometimes those are a little bit, the side lengths or the angles aren't uniform. Okay, going into some examples and non-examples. A good example of the Platonic solids would actually be Dungeons and Dragon dice, because they contain all the Platonic solids in their dice set with the exception of two irregular ones. But you can see we have the cube, the octahedron, the icosahedron, the dodecahedron, and the tetrahedron. And then some non-examples that we can go into is anything that has a curved shape. Polyhedrons cannot physically curve or bend in any way. They have to be flat planes, and they have to have sharp vertices. While the cone does have sharp vertices at the end, it does curve, so it's not considered a polyhedron. So let's get a little bit further into what are the Platonic solids. So first we have the tetrahedron, and it contains four faces, six edges, and four vertices, with three faces meeting at each vertex. And it's made up of equilateral triangles, which has the same angle measurement of 45 degrees on each angle. So the hexahedron, or otherwise known as the cube, contains six faces, 12 edges, and 8 vertices, and has three faces meeting at each vertices. And the faces are squares, and they contain the same angle measurement at each of the four corners, and it's a measurement of 90 degrees. The octahedron, which contains 8 faces, 12 edges, and 6 vertices, with 4 faces meeting at each vertices. And again, each triangle is an equilateral triangle, and the angle measurement is a 45-degree angle. The dodecahedron is a polyhedron that is made up of pentagons, and each interior angle measures about 108 degrees, and it has 12 faces, 30 edges, and 20 vertices, and 3 faces meeting at each vertex. Finally, the icosahedron, which has 20 faces, 30 edges, 12 vertices, and 5 faces meeting at each vertices. It is made up of equilateral triangles, which we specified has angles of 45 degrees. So we're going to get into some of the axioms of the Platonic solids. These are just general rules that all Platonic solids have to follow in order to be considered a Platonic solid. So first one is that they're only made up of one regular polygon, so they can't have a mixture of like triangles, squares, pentagons, etc. And they must have a uniform amount of faces meeting at each vertex. And it has to be greater than 3. So you can't have a mixture of maybe 4 faces at one point and then 3 faces at another. And as I stated before, these faces cannot bend or leave any empty space, and the sum of each vertex must be less than 360 degrees. So you might be wondering, why are there only 5? I have a video demonstration right here in the corner that I will expand for us so I can get into further explanation. But before we get into that, it's important to note that each axiom comes with like a price. For example, it being the uniform polygons, we cannot have shapes with multiple faces. For example, a soccer ball has a mix of pentagons and hexagons. That is not considered a polyhedron, even though it has a little bit of uniformity in it, because it has a mixture. And we cannot have multiple different faces meeting at each vertex. I stated before, like one has 3 faces and the other has 4 at each vertex. And this also risks another axiom of exceeding 360 degrees. I also stated Platonic solids cannot bend because, as we stated in our knot examples, they cannot have any spherical shape. They can also not perfectly align side by side with one another, because as when we get into our video demonstration, you'll see that it becomes a flat plane and it will be exactly 360 degrees, which is making it not a Platonic solid. Also, you may wonder why we can't use other polygons like hexagons or octagons to construct Platonic solids, and the more formal reasoning for this is that it will require a mix of other polygons. Like I said with the soccer ball, it also contains pentagons to construct a 3D shape. And any polygon that exceeds 5 sides runs the risk of exceeding the rule of being less than 360 degrees, and it will, like I said before, create a flat plane instead of a 3D shape. So this is the part where we get into our proof. The proof is a little bit more informal. So what I'm going to be doing is going into a demonstration of how each polygon, we'll talk about the side lengths and why we can't have less than the amount of sides for each Platonic solid or more, because it simply would not work. They would either leave empty space, overlap, or bend. So starting out, we have just a regular solid triangle. Obviously, we can't work with one triangle because it's just going to become a flat plane. And then next, we have a 2-sided triangle, and then when you fold it at its edge, it's just going to become another singular triangle, and that's not going to work either. And we also have a 3-sided attempt at a Platonic solid. And when we fold it over, you can see that it leaves an empty space that cannot form anything without being bent. But you might notice that this actually forms a Platonic solid if we add another side to it. So when it has 4 sides, it actually becomes our tetrahedron. And you'll notice that it has 3 sides meeting at each vertex. Now we have 5 sides, and when we fold this one, you'll see it leaves a lot of empty space right around the bottom part. So this also cannot work. Now, of course, we have 6 sides, and we'll see as we construct it that it won't be able to work. So you might say, oh, this creates a 3D shape. However, it actually has an irregular amount of faces meeting at each vertices. So the top sides have 3, while the sides have 4. So this breaks one of our axioms and therefore cannot be considered a Platonic solid. So this has 7, and when we fold this one, you'll actually start to notice that we're starting to get closer to our next Platonic solid, which is the octahedron. You can see there's a little space for another triangle right there, which is why it will eventually become the octahedron. So yeah, 8 sides, and when we fold it, it becomes the octahedron. So therefore our octahedron exists because it has 4 faces meeting at each vertices. Now we're adding a few more triangles to our octahedron to see what we can create with it. But again, this is not going to really work. However, you'll notice that when we're forming it, it'll start to overlap some of the faces. So of course this won't work. And now we have an even bigger one with more triangles. And you'll start to notice around this point that this shape kind of looks familiar, and it actually looks a lot like, as we keep folding it because we can see that that didn't work, it looks like our last polyhedron that's made up of triangles, which is the icosahedron, because you can see as I'm forming it, it has a 5-sided edge where 5 faces meet at a point right about there. But you can see that this does not work. Yeah, so there we have, when we add more sides, we get our icosahedron where it has 5 faces meeting at each point. And I can show you that it is uniform on all sides. Okay, next we're moving into squares. So again, we have just a singular square, it's just a flat plane, doesn't really do much for us. Now we have a 2-sided square, and again, this also doesn't do much. We can create like a little L shape with it, but you know, it needs to be enclosed, but when we fold it all the way, it just becomes another singular square. Now again, 3-sided. This doesn't really work either. We can create like a little U shape with it, but if we were to touch each point, it leaves space for 2 triangles, and as we stated before, this breaks one of our axioms that states that all the polygons have to be uniform. So this also doesn't work. Now, we did another demonstration with a set of squares that are like side by side. This doesn't work either because we can't fold it without making it flat, and even if you try to like curve it, as I said before, they can't really bend like this or like curve without breaking one of the rules. And this is another 4-sided one, except in a longer thing, and you can see that it's starting to look a little bit like a cube. So I'm showing you that the cube is that it wouldn't work for what is it, five-sided, because that will also become the cube. And I'm showing you what it looks like when it is all laid out. And we are adding a couple more squares to show that adding more does not work. It's going to create a rectangular shape, but as you put two flats together, that makes irregularity with the angles and the vertices. So even when you're adding more and more, you can see that I'm starting to add more and trying different orientations to make it work, but it's simply not going to work. And if you add enough, it'll just become a bigger cube. So it proves that the only uniform shape that we can have is the cube. I'm also pointing out that the vertices don't exactly line up when we're adding things together. Okay, now moving on to our pentagon. Pentagon is actually a more specific case that we'll get into. I'm showing again that two-sided doesn't work, but because the pentagon has a angle degree of 108, you'll see as we continue going, it's very much impossible to create anything but the dodecahedron with the pentagon, because we don't want to break our rule of exceeding 360 degrees. And as you can see there, when we're folding things up, that creates other shapes like triangles, which we also cannot have because they need to be a uniform shape. And I'm showing you that they can't bend together with this one either. It leaves empty space and it forces the pentagons to fold. We're getting into a more complicated example, but as you're folding this, you may notice that we can't have this without folding all the pieces inward, but it's starting to look, again, a little familiar. Now I'm continuing with adding more and more pentagons to try to make it work, but as you can see, it is simply impossible to try and create more than one. It creates a square space, which, as we stated before, we cannot have. And it also leaves a little bit more empty space on that little hanging one. Showing again that this doesn't work. This is where they start to get really overlappy, and there is a lot of empty space. And you can see I'm trying to find another orientation for it to make it work, but it will simply never work. So that the only orientation for the flat that will work, I believe you will see right now, we have our dodecahedron, where it has three pentagon meeting at a point, and this is the only orientation for it that will create a 3D shape that follows all of our axioms. It must be three because, as I stated, we can't exceed 108 degrees for each of the little angles. And that is the end of our video. So I wanted to show you also what the Platonic solids look like when they're laid out flat. You might have noticed from the video, I know I didn't show some of them, however, this is the tetrahedron, the cube, obviously, the octahedron, the dodecahedron, and the icosahedron. So there's our video link. So this concludes my presentation. Here's a cute little Valentine's Day drink. I really hope that you guys enjoyed and learned a lot as to the reasoning why there can only be 5 Platonic solids. And I hope you guys have a good time with the homework. I think it should be relatively simple. And here are my references. Easy. So anyway, have a good rest of your day, everyone. Thank you.